defense, the public defense. Let me introduce the committee, which has been chosen by the faculty of the school. So the evaluator reviewers are going to be Alzyod, PhD, and Joseph PhD. The members are Csaba Rögtör, PhD, Csaba Ekei, PhD. Our secretary is going to be Dr. András Lakatos, PhD, and I'm going to be today the head of the committee. First of all, I need to ask the candidate, is this totally appropriate or do you feel any offense?
No,
thank you very much. Then I would like to inform you that about the procedure that is going to be here today in the public defense. First, I'm going to ask Dr. András Lakatos to read out your CV to introduce you to the audience. Then I would like to ask you after that to make it as a presentation about your PhD thesis, approximately 15, maximum 20 minutes, focusing on your own results, focusing on your thesis points. Then I would like to ask the evaluators to read out the review they have made about your dissertation. Then you will need to answer the questions. Then I am going to open the public defense. So if the committee have any question, you will have to answer it. After that, the audience might have some questions. Then after the questions, I will let the audience, if they have any remark to your work. And finally, I would like to ask the supervisor to speak a little bit about your thesis, your work. Then I will close the public defense. I will ask everyone to leave the room. We are going to evaluate your work. Then I will be opening the public defense, and then we are going to tell the result. Is it okay? Can I wait for you?
everything is clear.
Thank you very much. So now I would like to ask our Secretary, Dr. András Lakatos, to introduce you to the audience. Thank you.
Thank you very much. Hussein Mohammed Alzyod was born in 1986 in Jordan, and his working experiences cover as science teacher, automotive maintenance manager, and service manager too. His education was quite wide too, because he made his mechatronics engineering PhD level degree in Jordan. After that, he passed the mechatronic engineering MSc level here in Hungary, in the Óbuda University, and after that, I am sure that now he will pass the doctoral school of Kandó-Kálmán doctoral school. The candidate has passed the requirements of the Kandó-Kálmán doctoral school because he has 23 publications connected to the dissertation. From that, one is D1 category, 2 of them is Q1 category, 4 of them are Q2 category, and 8 publications with impact factor, what the candidate has done. Thank you very much.
Congratulations for the magnificent publications.
Thank you.
For you and for your supervisor. And now it is the time to please present your research area. What have you done in the last 4 years, focusing on your own result, on your thesis, please.
Okay, thank you. Good afternoon, everyone, and thank you for being here today. My research topic is investigation the impact of printing parameters to enhance properties in additive manufacturing technology. As you can see here, the additive manufacturing can be categorized into main 7 categories: the introducing direct energy deposition, material extrusion, material jetting, powder bed diffusion, and sheet lamination, and finally DPP. And among these categories, my research focused on material extrusions, which is called also fused filament fabrication or fused deposition modeling. And as you can see here, it's filament based, heating by heater block, and then deposited to the plate through the nozzle. As we know, the additive manufacturing technology, especially the material extrusion, has many parameters that can be controlled, and each parameter has many levels. So it's not easy to control and investigate all the parameters together because you want to see the response of that. So because sometimes the response could be time, you want to measure time. Sometimes you need to enhance the properties, and sometimes you need to minimize the cost or the overall quality. And the motivation of my research topic was residual stress optimizations, because it's one of the main issues in the manufacturing technology. The second one, combined parameters influence. Under explored parameters, I found in the literature there are some parameters still insufficiently studied, and also material specific insights, support structural optimization, impact printing both, and post-processing innovation. And as we can see here from the chart flow, this is the dissertation approach. My dissertation was divided into two approaches. The numerical approach is focused on residual stress and warming deformation. And for the experimental approach, I investigated the ultimate tensile strength, the compression strength, flexural strength, and impact strength, and the surface roughness. I investigated 5 different parameters, materials, and I investigated 9 different parameters. Also, I made 2 additional investigations, the printing with pose, because it wasn't studied before, and the ironing post-processing. The characterization methods that I used in my dissertation were the mechanical testing, surface roughness stylus, tester stylus, finite element modeling, design of experiment, imaging microscope, and statistical analysis and optical profilometer. So, for my results, my dissertation was divided into main 7 thesis points. The first thesis point, the proposed hypothesis was there might be a significant impact on the manufacturing, structural, and thermal parameters on the value of residual stress, and the thermal aspect of material extrusion don't significantly contribute to residual stress. At the beginning, let's talk about residual stress. Because of the process of the 3D printing, there's quick heat loss from the top layers because it's deposited and leads to shrinkage. These constraints by the underlayer, it's preventing the full deformation of the new layer. So the residual stress results from this material constraint shrinkage tendency. For the first phase point, I made 3 different studies to study the parameters. The first study was focused into 2 structural parameters and 4 manufacturing parameters. The structural parameters were the infill density, infill pattern, and the manufacturing parameters, layer thickness, printing temperature, bed temperature, and printing speed. I studied 3 different levels for each parameter, and the results showed that for the structural parameters, there is slightly positive correlation between the infill density and the residual stress, while the infill pattern does not have any significant impact on the residual stress value. For the manufacturing parameters, I found that the layer thickness and printing speed negatively correlated with the value of residual stress, and the temperature, the printing temperature was slightly positive correlated, while the bed platform temperature does not have any impact. And here you can see the visualization of the software and simulation and the actual printed part, and this is the side view to see the warping deformation. For the second study, I investigated the thermal parameters. As we can know, the heat can be transferred through 3 mechanisms: the convection, conduction, and radiation. So for the conduction heat transfer, I investigated the printing temperature, also bed temperature because it controls the convection and conduction heat transfer, and I investigated the chamber temperature because it affects the radiation, heat transfer, and printing speed because it affects all the 3 heat transfer mechanisms. In this study, I studied 3 different levels for each parameter. I used design of experiment, and as you know, it's a structural approach to determine the relationship between input and output. From the design of experiment, I used the Cauchy method because it depends on minimizing the variation to improve the quality. And the results showed that the printing temperature was the most dominant factor, with about 60% contribution for minimizing the residual stress, and followed by printing speed and chamber temperature was about 20%, and the bed temperature is down 1%. For the third study, I investigated the structural parameters. The printing orientation, raster angle, and infill pattern with 3 different levels. And the results showed that the printing orientation was the most dominant factor also, with about 66.7%, while on the raster angle 25%, and the infill patterns also does not have any impact. So, for thesis number 1, I investigated the influence of manufacturing, structural, and thermal parameters on residual stress in material extrusion printed ABS samples, using the method manufacturing and 3 distinct models to address different aspects of process. First, I designed a bridge model to study how manufacturing and structural parameters affect residual stress levels. Through this model, I observed a significant impact of parameters such as their thickness and infill density. For the thermal investigation, I employed the Cauchy orthogonal array methodology to analyze a 3D component model, examining the relationship between thermal parameter and distribution of residual stress, and found printing temperature was the most dominant parameter. Moreover, I utilized the loop-bone model for further explore how structural parameters affect residual stress, particularly focusing on orientation effect. And here is the list of publications related to thesis number 1. For thesis number 2, the proposed hypothesis that the use of Cauchy orthogonal array to optimize thermal parameter could significantly reduce the warping deformation in material extrusion of 3D printing the ABS parts. In this thesis, I investigated 4 different thermal parameters with 3 levels, and I found that the bed temperature was the most dominant factor with about 47% of contribution, and the chamber temperature was the second one with 30%, and for printing temperature and printing speed, about 11%. Also, I found the optimal levels of each parameters. For the printing, the bed temperature was 87 degrees Celsius. For the printing speed, 30 millimeters per second. For the chamber temperature, 37 degrees Celsius, and for the printing temperature, 235 degrees Celsius. So, thesis number 2 stated that I used the Cauchy orthogonal array to reveal thermal parameters to minimize warping deformation and enhance the overall performance of ABS printed parts made using material extrusion. Moreover, I minimized the warping deformation using the optimal parameters levels. And the related publication for this thesis point. The third thesis point, the hypothesis states that there might be a significant relationship between 5 example printing parameters: the printing speed, infill density, printing temperature, layer thickness, and bed temperature, and the warping deformation response of material extrusion using TA polyamide 12 material. And for this thesis point, I found the literature that these are the parameters wasn't sufficiently investigated and this type of material. So I investigated 3 levels of each parameter. I employed the Cauchy orthogonal array for this investigation, and I found that the bed temperature was the most significant factor with about 82% of contribution, while the other less than 5%. Moreover, the optimal levels for this research was, as we can see here, the infill density 20%, the printing speed 100 millimeters per second, printing temperature 240 degrees, layer thickness 0.2 millimeter, and bed temperature 100 degrees Celsius. So, thesis number 3 stated that I utilized the Cauchy orthogonal array combined with ANOVA to determine the effect of 5 printing parameters: printing speed, infill density, printing temperature, layer thickness, and bed temperature, on the warping deformation response of the material extrusion using PA12 material. Furthermore, I successfully identified the optimal parameter levels that resulted in the lowest mean warping deformation, effectively minimizing warping in the process. And I will publish my results in a Q1 journal article. For thesis number 4, the idea really came from my supervisor about to investigate how many multiple materials can affect the parameters. So, in this investigation, we want to see if the parameter is material dependent or not material dependent. So, the hypothesis of that was there might be a material dependent influence of common printing parameters on the level of residual stress and warping deformation of material extrusion parts. I investigated 6 different parameters with 3 different materials, PAI, ABS, and PA6, with 3 levels of each parameter. And the result for residual stress was, regarding the layer thickness, for the PAI and ABS, it was the most influential factor. And that's give indication that this parameter is less sensitive to material differences. For printing temperature, I found that the highest influence residual stress was in PA6, and that means a precise control for this parameter for optimal results. For the infill density, across all the 3 materials, it was moderate noticeable effect of the residual stress and more sensitive to material differences. Regarding the rest parameters, printing speed, bed temperature, and infill density, exert a minimal influence in residual stress across all materials. Regarding the warping deformation, I found that the infill pattern was a significant contributor in all 3 materials, so it's material independent factor. For the layer thickness in PAI, it was contributed significantly, while in the other, one need to find tuning. For printing temperature, the result was a little bit different. For low, it was relatively low for the PA6, moderate for ABS, and high for PEI, and that suggests that printing temperature is more material dependent. For the rest of parameters, the printing speed, infill density, and bed temperature, it's found that the material dependent sensitivities to these factors. So here's number 4 stated that I wrote the issue of orthogonal array and finite element analysis and found that some of the printing parameters, printing temperature, printing speed, bed temperature, infill density, layer thickness, and infill pattern are material dependent, influencing the residual stress and warping deformation of parts fabricated with the material extrusion technology. For thesis number 5, the proposed hypothesis that the different printing methods and printing with pose could significantly have a similar ultimate tensile strength. And for this investigation, I investigated 2 different orientations, vertical and horizontal, and printing with pose and printing continuously as a normal print. And I found that, as you can see here, figure A and B, this is for the horizontal printing. I found that printing with pose or without pose does not have any impact, and the ultimate tensile strength was about 47 megapascal. While in printing in vertical orientation, the magnitude of the ultimate tensile strength was about 50%. It was 24 megapascal, and with the pose, it was less than 11 megapascal. So thesis number 5 stated that I investigated the impact of printing orientation and printing with pose on the UTS, and found that the printing orientation as well as continuous printing and the printing with poses have affected the UTS of PLA parts manufacturing using material extrusion technology. For thesis number 6, there are 2 proposed hypotheses. The hypothesis number 1 was, or hypothesis number 6 was, the average roughness of PLA samples produced can be enhanced using the iron post-processing technique. The second hypothesis, the 7th hypothesis, the contact and non-contact RPA measurements method may yield incomparable results under certain conditions. In this thesis point, I investigated the effect of ironing post-processing on the value of average roughness. I also studied the difference between the contact measurements method and non-contact measurements method. So I studied the three factors or parameters for the ironing post-processing: back speed, ironing spacing, and flow rate, with 4 different levels, and I studied every parameter independently. Applying the ironing post-processing with the default setting, I minimized the surface roughness with a contact method about 83%, and I successfully optimized with the non-contact measurements method about 80% of reduction. For each parameter independently, I found that the path speed slightly positively correlated with the value of average surface roughness. And for the ironing spacing, I found it strongly positively correlated with the value of ironing spacing. It's positively correlated with the value of average surface roughness. For the flow rate, I found that it's slightly positively correlated with the value of surface roughness. And here we can see the magnified top surface of the optical profilometry. You can see without ironing how the surface, and this after the ironing. And here you can see how each parameter independent investigated. And we can see obviously that increasing the ironing spacing was the most important factor in minimizing the surface roughness. So I investigated different levels of ironing parameters. With the investigation of all parameters and levels, I successfully minimized the average roughness from 9.63 micrometer to 1.31, with about 86% of reduction. And using the contact method, and with the non-contact method, with about 81% of reduction. Also, I found that the contact measurement has some limitation, which including the potential to scratch soft materials. And also, it has some limitations with the investigation of the low values of the surface roughness because of the tip of the stylus. Non-destructive method measurement, it's the non-contact, it's a non-destructive method and can be fast and accurate results. So, thesis number 6 stated that I minimized the surface roughness of PLA samples manufactured from material extrusion using an ironing post-processing technique. Additionally, I found that different ironing post-processing parameters levels affect the RA value. The results indicate that ironing spacing has the most significant effect on the average roughness. Furthermore, I utilized both contact and non-contact measurement methods, allowing for comprehensive examination of their respective limitations and accuracy in characterizing surface roughness. And this is application related to my thesis point. For the last thesis point, thesis number 7, I investigated the proposed hypothesis that implementing iron post-processing could enhance the mechanical properties of the material extrusion part. And for this investigation, I used the Hooks-Benkin design, which a type of response service methodology. And I investigated the tensile strength, impact strength, and flexural strength, surface roughness, and compressive strength. And I used the 3 parameters with 3 levels of each parameter. So for the ultimate tensile strength, I increased the value from 43 megapascal to 56 megapascal with about 28% of increasing. For the flexural strength, it was increased about 35% from 63 to 85%, 85 megapascal. For the compressive strength, I improved it from 62 to 78 megapascal with about 25%. For the impact strength, it was significantly rose from 3.7 kilojoule per meter square to 9.84 kilojoule per meter square with about 161% of increase. The iron for the surface roughness, it was decreased by about 70% from 8.8 micrometer to 2.73 micrometer. And here we can see the micrographs of the cross-sectional area fracture without ironing and with applying after ironing. Here we can see the tensile, how the voids affect and how it was eliminated after applying the ironing post-processing. So thesis number 7 stated that I applied the box printing design to investigate the impact of the printing process on mechanical properties of material extrusion samples. I found that iron processing enhanced the overall properties of the printed samples, and the spacing between spaces was the most significant parameter. And here's the publication I published my result in the Q1 Journal Impact Factor. And the practical usage of my research and my investigation was the high quality work on warp-free parts, material specific insights, printing orientation, and improved aesthetic value, improved the surface finish, and balance the trades off and the cost efficiency. For the future work, the cost efficiency, material compatibility, in-depth surface characterization, hybrid processing techniques, additive and subtractive manufacturing integration. And after submission my dissertation, I worked on my future work, and I successfully published a Q1 Impact Factor journal to investigate additive and subtractive manufacturing integration. And also I published another paper in the cost efficiency investigation. That was after submission of the dissertation. So, and here this is list of my publication. And thank you for your listening. I hope that I was good, but
Thank you very much for the presentation and keeping the time. And now I would like to ask Alzyod to make his review. As the candidate received the review, you might shorten the review if it's possible.
Okay, I will try. Nowadays, additive manufacturing is a very frequently researched topic, as there are so many potentials in this technology, and researchers still do not know everything about it. Besides, engineers always try to find the best solution for the given problem. If there is an existing solution for a problem, they will improve it. So we can say that the topic of the dissertation is quite a significant detail of the AM problems. Okay, then I will not read about parts of the dissertation, but I state that the candidate knows and correctly applies the rules of English grammar. The overall organization of the dissertation is logical and clear, easy to understand and follow. The opponent likes the structure of the dissertation very much. How much should I shorten? Very short. Okay. So I also stated that which chapters are in the work, and then I skip to the last page. Okay. In chapter 9, the candidate summarizes the thesis of the dissertation and introduces the practical usage of his scientific results. The candidate also outlines the possible future works, and the opponent accepts the candidate's thesis. The dissertation is a very deep work, both from the point of view of the literary background and on the side of the candidate's own research. He used up-to-date models and methods for his work. Of course, the possibility of using different types of printers also have the significance of his work. And now my questions. Nowadays, circular economy is getting more and more important. In chapter 4, the candidate also mentions that PA12 can be a suitable choice for both circular economy and 3D printing application. The opponent has the following question to this part. What makes you think that PA12 can be a suitable choice for circular economy? how can be this material, maybe better than other filament materials, suitable for the philosophy of the circular economy or circular manufacturing? And during your examinations, you dealt with only one problem at a time on special specimens for the given analysis. In the real life, in case of engineering tasks, the engineer faces with more complex questions. Based on your examinations, do you have any idea how to implement your results to a more complex part of a machine element? For example, determining tooth bending stress in case of a printed gear. The opponent declares the following. The thesis contains authentic data. The thesis is the candidate's own work, and the thesis can be submitted to the public debate. So this was a very excellent
Thank you very much. And now I would like to ask the candidate to answer directly the questions, please.
Okay, thank you so much for your review of my dissertation. I will go to the first questions about the polyamide 12, why it's suitable. The first, it's a soluble material. It can be from biocircular raw material like waste oil, waste cooking oil. The second thing, it's recyclability. So it can be recyclable without any degradation of its mechanical properties. The third thing is the low environmental impact because it can have lower carbon footprints. And durability and longevity, it has long lifespan, so the time of recycling will be minimized or will be less than the other materials. And lower moisture absorption. This material has lower moisture absorption, so it can maintain its properties over time and reduce the material degradation. That also it was compatible with the other manufacturing technology. So the overall of these materials with the low moisture, so it can be the lifespan more, the recycling is less, and for after the recycling, this material because it has a high tensile strength, abrasive strength, and impact resistance, so it can be recycled multiple times without any that much degradation. For the second questions, and really it was a little bit hard questions to answer it because the complex geometries, the industrial impact, how to implement that. First of all, as you saw in my dissertation, I investigated most of the parameters set individually to see the impact of each set of parameters on the residual stress value. So after that, these parameters can be transferred as a linear condition or a linear input to another printing, like the raster angle or ear orientation can be guided for printing other parts like the gears. And also the adaptability. So also the gear can be imported as a CAD or a step file to the simulation and can study the critical residual stress critical points like the tooth roots. And finally, the multi-physics coupling. The DigiMat simulation can predict the residual stress, warping deformation, and temperature history. And these data can be exported to other simulation or other software finite element analysis like Abacus or ANSYS as initial conditions, and after that I can apply bending or operational load to analyze the full stress analysis. So this is the answer of the second question. I hope that you accept.
Thank you very much. I need to ask if you would accept the answer. Thank you very much. Now we would like to continue, and I would like to ask Joseph Zilka to read your evaluation.
Thank you, dear participants. Welcome, everyone. Thank you for the invitation to review the candidate's dissertation, of course. As we also heard of, for the opinion of Ányos Takács, I had the same positive feeling about the candidate's work. I will highlight the main parts of my remarks, but almost totally, because of course the candidate and the committee members know my review, but attendees don't hear that yet. Now they will hear it. So the PhD dissertation is a summary of the results of the scientific research of the PhD candidate. The dissertation layout is fully meets the doctoral regulations, having lists of tables, figures, abbreviations, and publications inside. In addition to the contents and the list of figures, tables, and abbreviation, the PhD thesis contains 9 chapters, followed by the references and appendixes. The full length of the doctoral dissertation is 132 pages. The core text is 88 pages, followed by the references, which is very good. I think it's 208 items in it. And finally, the other appendix A, B, and C is 21 pages. Of course, it's the results. The readers see that this is the homework of the candidate. The authors focus on the additive technology in a narrower sense, the effects on the manufacturing parameters in case of material exclusions. The authors set up 7 theses, thesis 1, 2, 3, and 4 based on simulation techniques. Theses 5, 6, and 7 are dealing with manufacturing and materials testing on the author's specimens. The chosen research topic is current. Additive manufacturing is constantly growing and improving the manufactured parts functionality and their properties is important. So the structure of the dissertation is correct, the readability is flawless, there are hardly any typos in it, but there are some spelling mistakes. The internal logic is not the traditional Hungarian type, but adequate. The research methodology is good. The candidate used statistical and design of experiment methods to formulate statements between the examined parameters. We see that in the candidate's presentation. As András Lakatos presented, the candidate listed a lot of publications connected to the dissertation and the thesis. In chapter 1, the candidate introduced the subject of the dissertation, the motivation, and the main objectives. In every chapter, from chapter 2 to chapter 8, the author deals with different fields of the research. In these chapters, at the beginning, there is a literature review, and after that, the author explains their own research topic, and at the end, the author states his thesis. In chapter 2, the author made the Digimat AM simulations on different part geometries using ABS material model. The focus of the examination is residual stress. The results are also presented in colored residual stress maps, which shows the residual stress distributions in the test parts. I have a question with this thing. Why does the maximum residual stress form at the center of the surface of the breached parts leg? It can be seen in figure 2.6 in the dissertation. In connection with this research work, thesis 1 is acceptable with the additional information in chapter 9, which follows this thesis. I also had the luck to be here during the home defense, and at that time, the bigger theses seemed better to me, but in the final dissertation, there is a chapter 9, which contains this description following the theses, and these descriptions contains a lot of important information about the parameters of the measurement. So with this chapter 9 descriptions, the theses are good for me. In chapter 3, the author explained his thermal evaluation of material extruded process parameters and their impact on warping deformation of EBS parts. Used Digimat AM to simulate some parameter sets and created a signal to noise ratio calculations to show the process parameters, which creates the smallest warping effects. In connection with this, thesis 2 is about the warpage of the manufactured parts based on Digimat AM simulation studies. The content of thesis 2 is acceptable. However, the definition of the parameter limits of investigations are missing, and in chapter 9, at the description, the reader can find that information. In chapter 4, the author made another simulation analysis with different printed parameters to enhance the part quality, finding the optimal manufacturing parameters as we saw in the presentation. I have another question in connection with this. In case of 3D shaped cuboid model simulation, did you support the manufactured model or built on the base plate of the FFF machine? Do the supports have effect on the warpage formation? With this research field, thesis fee is acceptable with the additional information in chapter 9, which follows the thesis. It can be stated that it is a new result. It is a new result with this exact material, manufacturing parameter, and research methodology. In chapter 5, the author explains these results of how different manufacturing parameters affect on samples properties manufactured by different materials, PE, ABS, and PA6. Thesis 4 is acceptable according to the results explained in the dissertation with additional information in chapter 9, which follows this thesis. In chapter 6, the author explained the results of different layer orientation on UTS and Young's modulus of 3D printed PLA and the effect of pausing the building process on UTS and Young's modulus of the 3D printed PLA material. In connection with this, the thesis file is acceptable based on the experimental work and the statistical evaluation with the additional information in chapter 9, which follows the thesis. In chapter 7, the author go around the subject of ironing process for the usage to make the surface smoother and define the surface roughness parameters. Thesis 6 is acceptable according to the results explained in the dissertation with additional information in chapter 9. In chapter 8, the author did mechanical tests on material excluded parts to examine the effects of ironing post-processing on the mechanical properties, and in connection with that, thesis 7 is acceptable according to the results explained in the dissertation with the additional information in chapter 9, which follows this thesis. The references, as I said before, satisfying the 208 referenced item contains mostly articles which are appropriate, up-to-date, and relevant. It contains the basic scientific works and the latest papers, as well from prestigious journals. So I need to summarize the whole thing. The candidate presented a great dissertation work, providing that he can fulfill the requirements of a PhD title. The candidate has demonstrated the general applicability of the measurements and testing methodology. The theoretical and practical considerations presented in the dissertation are the candidate's original work, I think, and what I saw during Hussein's work. Taken together, the dissertation meet the requirements of the Kando-Kalman Doctoral School and the Budapest University of Technology and Economics. The candidate has proven to possess comprehensive professional knowledge and skills necessary for the independent scientific research. The theses were published by the candidate, and I accept them as new scientific results. Based on the thesis points, I recommend, based on these points, not the theses, but I can say that I accept all the theses, so of course these are good too. I recommend that Hussein Alzyod PhD dissertation be submitted for the public defense. Of course, they are here, and upon the successful defense, I propose to award the PhD degree.
Thank you very much, Dr. Mika, for the very detailed review. And now I would like to ask the candidate to answer the remaining questions.
Thank you so much for the review. Regarding the first questions, I really was expecting this question from the review of the journal, but it came from you. As you can see here, I used this bridge geometry, and the maximum residual stress, as you mentioned, it was in the pillar in the leg.
Yep.
So the clarification for that, the shrinkage and deformation during the cooling, it's induced the bending effect. So it happens because of the bending effect that induced because of the shrinkage and deformation during cooling. Then there's a thermal, differential thermal contraction between layers, because printing layer upon layer is caused the pillar to resist the natural shrinkage of the upper part when printing the top part of the bridge. And this resistance creates tensile stress and compressive stress. The tensile in the outer surface and the compressive in the inner surface. I mean the outer surface of the leg itself, not the bridge, because the out part it will be less. As you can see, if you take the leg as independent part, so you can see the line here from here, it's the cause of the bending stress, the compressive from inside and the tensile from outer surface. And as I mentioned, this is the real part that I printed, and you can see and you can feel the bending effect of this part. and you can see it by yourself. You can see how the deformation affect and the bending affect the residual stress value. Regarding the second question, in case of 3D shapes cuboid model, there is no support in the simulation. This is one of the limitations of the Digimat as manufacturing, that it was built directly to the plate. Even if you add support structures, it will not simulate it, because in the Digimat simulation, importing the part, it should be in a step, as a step file in one step, and importing the path, it can be in another step, not the same step, from the slicer software as a G code. And when importing this, you have to align the printing path or path printing to the part itself. So any path printing out of the part geometry, it will not be simulated. And here also, I tried it to print with support. So real printing was like this, full bridge, without any deformation and without any bending. But in the software, it showed me there's the bending effect. So this is one of the limitations of the Digimat manufacturing. So there's no support and there's no structure can be simulated.
Okay, thank you.
The answer of two questions, if you can.
I have a little question about the first question. And what do you think we can see here in figure 1 a colored stressed map? We can see that in every section of this part, in the we can see that this distribution of stresses are created. So in every, not just the front of the part, so in every section, we can see that this is the stress.
Yes, because it's layer upon layer, so the stress distribution will be the same.
Okay. Okay, thank you.
Can you accept the answers?
Yes.
Thank you very much. And now I would like to ask our secretary to read out loud the question from the committee, and then you have to answer it.
Thank you very much. The committee's question is, in general, does the use of supports have an effect on deformation? I will give you
Yes. Can I read the question? In general, does use of support have an effect on a deformation? This is the question.
Yes.
Yes. From the experimental point of view, when we investigated the support structures, can minimize the warping deformation, and there's many types of supports like skirt or beam, or some printers they use some stick materials to stick the part to the plate. And here, as you can see, the other part is with support structures, and it's fully good part without any deformation, without any bending.
Can you show us?
Yes.
Thank you very much for the answer. And I would like to ask the committee if we can accept the answer. Yes. Thank you very much. So, from the committee point of view, thank you for the answers. And now I would like to open the discussion and the public defense to the audience. First, those who are here, and then in second part, those who are online. So please, if you have any question, do not hesitate to make it to our candidate. And I would be grateful if you would introduce yourself for the minutes of the meeting. Thank you. It seems to be not much question from here. You are very lucky. And any question from the internet?
I will see the team.
Please investigate it.
If there anyone from the...
No question. That was excellent.
Thank you, sir.
I know this must be Professor Gorbash.
Yes.
Congratulations. It was excellent.
Thank you.
No question. Sorry.
Thank
Very
you,
good.
sir.
If there is no question, then we will move to the part of the remarks. Do we have anybody remarks from the audience here? Seem to be no. Do we have any remarks from the internet?
I think no.
Very good. Then I would like to ask the supervisor to conclude the last one, please.
Hua. Hua is a Hungarian expression.
Yes.
Hussein said why start with this expression. I met Hussein nearly 4 years ago as a proud father when he has started his PhD studies. I think it is very hard to start a 4-year period of PhD studies far from his children. I wanted to be sure, and I gave him requirements at least 2 or 3 times more than the official requirement. That was the first point when he started use this expression, "kuha." Because of this, he started to work very hard from early morning until late night, right from the start. He was a quick learner, and he applied very well what he had learned, and he has a brilliant master what he had learned, and even surpass requirements with his professional curiosity. He was very kind and helpful to me and the other, and his work attitude influenced to other international students. Like this, he became a true example to them. He helped them a lot. It's very important to mention, I think. It was clear in the second year that will be a success story. It was a pleasure to work with him, personally or online, both. I conducted him, I received almost immediate response. He became an expert in his area, theoretical and practical point of view, as a 3D printer technician, as a software developer and user. I think he's now a professional in this area. I have quickly mentioned his professional skills in the publishing area. He has to practice a lot, but very good results, I think. I feel he's excellent researcher, developer, scientist already, and I hope he will share this knowledge and his attitude to many people. And I hope I will as doctoral students like him.
Thank you.
In the future, I was glad to work with him. I learned a lot from him. Thank you very much.
Thank you, sir.
Thank you for the supervisor speech was really longer than the presentation of Thank you very much. I think you managed to convince the committee. Now I would like to close this session and we would like to ask everyone else who is attending to leave the room for a couple of minutes. We need to discuss the results and fill out the form.
Okay. Should I close the session?
Professor Vika is going to
Okay.
the microphone.